so this is problem number 6 from the AP Calculus AB for your response section. I'll give you a moment to read the problem, so you may want to pause the video now. Okay, so you're given an implicit equation, in this problem, and you're given the derivative of that thing. So there's no need to actually find the derivative. They've saved you some time here. And in part A, they say write an equation for the line tangent to the curve at the point -1, 1. So in order to write an equation of a tangent line, you need two pieces of information. You need a point of tangency, which they've given you here, -1, 1. And you need the slope at that point. And in order to find the slope of a tangent line, you plug the point into the derivative. So dy dx at the point, -1, 1, not -1, would be what I get when I plug that point into this derivative. So let's see, that would be y over 3y squared minus x. So that looks like it's 1/4, right? So then the equation of the line would be y minus 1 equals 1/4 times x minus -1, which is +1. Now you could write it in slope-intercept form, write it in point-slope form, who cares? This is an equation of a tangent line. That's part A. Now for part B. Part B says find the coordinates of all points on the curve at which the line tangent to the curve at that point is vertical. So if a line is vertical, then that means its slope is infinite. And if the slope is infinite, that means the denominator of the fraction is 0. So it's some sort of number over 0. Remember, we talked about that when we were doing limits. So what I want is a place where the denominator of the slope, which is 3y squared minus x, equals 0. So that happens when x equals 3y squared, which is fine, except that's a relationship between x and y, which by itself isn't enough to actually tell me what x or y actually are. So whichever point I have has to satisfy this, because that's what makes the slope vertical, but it also has to satisfy this, because it needs to be on the original function. So on the original function, slope being vertical. So what that is a system of equations. X equals 3y squared. So in this original equation, which was y cubed minus xy equals 2, everywhere I have an x, I can replace it with 3y squared. So that gives me y cubed minus 3y squared times y equals 2. And if I solve that for y, y cubed is -1. This is some weird arithmetic error, if that makes sense. So y would be -1. So y has to be -1. It also has to satisfy the other equation as well. So I'm going to plug it into the original equation. When I cube -1, x times -1 equals 2. So let's see, that would be -1 plus x equals 2. So the points on the curve where the line is vertical would be at 3, -1. Now if I were to plug -1, that white line, into this, I get x equals 3 as well. Same idea. So this is the answer to part B. So for part C says evaluate the second derivative at the point on the curve where x is -1 and y is 1. So since we need the second derivative, that is the derivative of the derivative, right? So this is an implicit differentiation problem with the derivative. So what I'm going to do here is I've got y over 3y squared minus x. So you know when we're doing implicit differentiation, the y is a function that's dependent on x. So I often will rewrite that with f of x's, so I don't forget. Now, in order to take the derivative of this thing, the derivative of the derivative is the second derivative. And on that right-hand side, I would need to use the quotient rule. So quotient rule says low 3f of x squared minus x, which would be 3y squared minus x, d high, which would be the derivative of f of x, which would be f prime, which in the Leibniz notation is dy dx, minus high, which would be f of x, which in the Leibniz notation is y, d low, which if I did the derivative of this thing, I would have to use the chain rule. And when I do the chain rule, the derivative of 3f of x squared would be 6 f of x to the first times the derivative of what's inside, which would be f prime of x, which is, in Leibniz notation, the f of x is y, and the f prime of x is dy dx. So this would be 6y dy dx minus the derivative of x with respect to x, which is 1, all over low. So that'd be 3y squared minus x quantity squared. Now this thing looks kind of intimidating, but I want you to know it's just a bunch of arithmetic, right? So I want to plug in x equals -1 and y equals 1. So when I plug in x equals -1 and y equals 1, let's see, this would be 3 times 1 squared minus -1 times dy dx, which we'll talk about in just a second, minus 1 times the quantity, 6 times 1 times dy dx, minus 1, all over 3 times 1 minus -1 quantity squared. Now notice everything in here is a number except the dy dx. However, we can actually replace that dy dx with its value at the point -1, 1 if we simply take that point and plug it into the derivative. Now the nice thing is we've already done that in this problem. We did it in part A. The derivative at -1, 1, which is again what we have here, is 1/4. So everywhere I see the dy dx, I'm going to replace it with 1/4 because that's the value of this derivative at -1. So let's see. This would be 3 plus 1, which is 4. dy dx is 1/4 minus 1 times 6 times 1/4 minus 1 all over 3 minus -1 is 4 squared, so that's 16. So 4 times 1/4 is 1. Minus 1 times, let's see, 6 times 1/4 is 3 halves, minus 1 is 1 half. That's all over 16. So that's 1/2 over 16, which is 1 over 32. So that's the answer to part C, and that's problem number 6.